And so over the last 5 years, we've been working on taking this original demonstration and really bringing it to a point that it could be massively deployed. So one of the things that we demonstrated early on is your ability to pick up relevant signals of interest. For example, if you slap this flexible electronic patch on your chest, we can do things like measure your ECG. We can also measure skin temperature, thinking about someone at risk for infection. And also me, remember, a newly coined neuroscientist/data scientist. My original motivation for developing these technologies was to be able to unobtrusively record electrical signals from the brain. And so we demonstrated early on our ability to pick up basic things, such as the alpha rhythm during eyes open and eyes closed. So all this looked good and dandy, and when I got to UCSD in 2011, I literally sprinted towards the medical school, really trying to take advantage of the fact that we have not only a strong engineering program, but we can really deploy this in the wild and really test it in a real clinical context. And so going back to the story of pregnancy, one of the things that we did early on is we tested our ability to measure with our flexible electronics the same type of signals you want to measure with these belts. So in this picture, what you see is a woman in labor at UCSD Medical Center, and she has the two clunky belts that are measuring the uterine contractions and the fetal heart rate, and simultaneously we have a multi-electrode array of these patches. And here our focus was not on demonstrating the fully wireless capabilities, but rather focusing only on their ability to sense the relevant physiologic signal. And so what you see in this picture here is the fetal heart rate, where the red is what comes from the clunky belts, and the blue is our estimate of the fetal heart rate coming from our flexible electronics and using some of our data science analytics algorithms. So all of this looked good and dandy, and in fact, we started to get bombarded by physicians at UCSD who wanted to deploy our technology for many purposes. But there was one problem, and the problem is that what I demonstrated to you on that original picture with that patch was very sexy and very cute. But building that system so that it robustly works was very cumbersome and very error-prone. And so our graduate student Day was an audience. Day, wave your hand. All right. This cute little dog. Day got very interested in taking our original approach that you see here in this picture, and I don't expect you to understand the details of this picture. The bottom line is it's complicated, and we wanted to replace this picture with a simpler picture in terms of how we did this process. And so what Day basically invented, necessity is the mother of all invention, is a much simpler process to arrive at the exact same result. And so we can build the exact same types of patches as you saw in that original picture, but in a manner that's much more scalable and much less error-prone. And so if you notice in the picture up top with the red X through it, there's all sorts of stuff where you have to dip in chemicals, etc. This area right here, this is where all the bottleneck was, and all sorts of extra time being spent. And if you take a look at Day's new approach, it only requires these standard clean room procedures. These are the same types of procedures that are routinely used in semiconductor manufacturing industry, so it suggested that this is much more scalable and indeed it more robustly works. And so what this speaks to is the importance, especially if we want to translate inventions outside of the lab, not just showing a moonshot capability, but really trying to think about how you could scale this more generally. What this speaks to is if we think about the Industrial Revolution, one good example of that is the invention of the printing press. And one of the things that Dave basically showed, as you can see in this video here, is the ability to peel off these electrodes just using a standard lint roller. So the high-level idea right here, which was very brilliant of Dave, which is that we ultimately are going to adhere these things to the skin with some type of typical adhesive. Why not use that adhesive also to peel it off of the wafer that we build it on? Some of our graduate students, who unfortunately is not here, he's probably in the lab, Yun-Sung, took another approach where he was able to take not only sensors, but also the integrated circuits for amplifying the data, digitizing it, processing it for encoding for wireless transmission. He's invented an approach where we can take any existing chip made in a certain format of outside companies and embed it inside of these flexible electronics. And to emphasize, this approach is compatible. What I'm sort of emphasizing here is not only what we can build, but how we can build it in a manner that's compatible with existing frameworks. And so what this starts to speak to is our ability to build scalable and cost-effective approaches to build these types of systems. And you can decouple the building of the sensor from the integration of the circuits that process the data, so everything is modularized. And so that's the story that I've sort of told you so far. But as we know, if we want to build a full system right here, we also need to think about the wireless aspects of this. And so in that regard, I can dive into that for a moment. And so in that regard, another one of our graduate students who just defended his PhD built a stretchable and flexible antenna. And the nice thing about this device is that you can package it inside of the same standard type of FDA-approved adhesive that is routinely used in hospital environments. And actually, it's the same type of stuff that we use for Dave's sensors. And so we basically use the standard fabrication approach that Dave used to build the sensors, but we're just changing the pattern. And where we started with this is building, basically taking the same design that's used inside of all of your cell phones, an inverted F antenna, and we wanted to turn that into a antenna that can actually bend and stretch. So if you notice, this has a mesh-type structure with different holes in it. And we started off, doing standard types of simulations to understand how the antenna works. And one of the other clever things that our former student Amr did is he invented an approach that really makes this an adaptable antenna. And what that means is that these antennas, we might want to mount on the human body, but we also might want to mount on an inanimate object, such as a piece of medication or something else. And so when you mount it on the human body, that has a different dielectric constant, so to speak, than another material. And he invented a very simple approach to tune the antenna, literally by just cutting it with a piece of scissors. So it's very nice. So we can optimize these antennas to mount onto whatever type of material that we want. And one of the things that he demonstrated in his PhD is his ability, in the case of mounting this on the human body, to build the antenna, mount it on the human body, and demonstrate that we can transmit via Bluetooth to a smartphone over 150 feet away. So very proud of Amr and his work, and he's now a big-time product guy at Texas Instruments. Hopefully they'll send us some free stuff. Well, what that speaks to here is now I've talked about the sensor and the IC integration, and now I've talked about the wireless antenna, and you guys might ask, well, Todd, are you also going to talk about the energy source? And the answer is, I'm a jack of many trades, but not all trades. So we're not innovating at all with batteries, but rather, if you take a look at all the innovation taking place by outside companies, increasingly, you can take existing batteries that are thin and flexible and directly integrate them into our process, and that's the approach that we take. One issue that does manifest itself that you have to think about, and this is another invention from one of our students, is the following. If you take a look at a lot of the work in the Internet of Things, right? Things, small things embedded in your house, or wearable technologies. The current workflow, or the common workflow, is that they digitize the data, they transmit the data to the quote-unquote cloud, and in the cloud, data is turned into information. That can create some challenges. And in particular, until Elon Musk figures out how to miniaturize batteries with lots of energy density, we still do have a big bottleneck, which is the processing of energy. And the most energy-draining aspect of these wireless systems is the actual wireless link. The processing does not consume as much energy as transmitting wireless, and so that creates a challenge. And so we got interested in these applications with wearables. Are there other, is this the only workflow that we have to attain? Can we turn data into information, but not in the cloud? Now, another challenge with this picture that you see is, let's imagine someone has something like an epileptic seizure, and you have this wearable, right? And this data has to be moved somewhere else before it's interpreted. That latency can be the difference between life and death. So for many purposes, we were interested in not always doing the analytics in the cloud. So our graduate student, Marcella, invented an approach to take advantage of the fact that, as we all know, the amount of computational power that's in your iPhone today is equivalent to what was in the supercomputers for Apollo 13 in the 1960s. So if we fast forward and we think about that, what's in our iPhone today is going to be in a small chip that we can embed inside of this wearable tomorrow. So with that in mind, Marcella took a look at current chips and what types of algorithms can we do and what types of interesting things that we do that we can actually quantify uncertainty and do all the processing right there in a chip that can be embedded inside of a wearable. And indeed, she demonstrated quite a few things that we can do. Very proud of her for this invention. And so this allows for much better energy efficiency because you're turning the data to information right where you acquire it. You only need to transmit data to the cloud sporadically. As I mentioned, it addresses the latency concern, and it also has an interesting implication from security, right, and privacy. A lot of people are concerned about the fact that if the Fortune 500 can get hacked, and if the federal government can get hacked, so can Kaiser Permanente, so can my doctor. And so in this situation, if the data is being turned into information locally, not all of my data is necessarily stored in the cloud. So in fact, what Marcella has done is even more interesting than that. She's built a suite of algorithms, cutting-edge approaches to quantify uncertainty for physiologic data sets, and shown that you can apply these in a cloud infrastructure, such as Amazon Web Services, or inside of the chips called GPUs in your smartphone, or inside of very energy-efficient chips that can be embedded inside of wearables. And in fact, she spent her summer at IBM Research working on one of their normal working chips, and just drove back to San Diego on Sunday. So what that means, when we add all